Okay, so today we're going to look again at that Lab 4.1, page 25 in your lab book. It's the simulation of Rutherford's gold foil experiment. Now these calculations that you've been doing don't really make any sense unless you understand what is really going on here. What are we trying to figure out? So we're looking at, in 1910, let's read this little paragraph here. In 1910, Rutherford's collaborator, well, you guys can read that. Basically, what happened is they wanted to pass an alpha particle through a gold foil. So we had our gold foil, and they fully expected that this alpha particle, or this alpha beam, would just go straight through the gold foil. But what they found out is every once in a while they had particles bouncing back. They had particles bouncing back. Okay. And so, therefore, this investigation, or this experiment, I guess you'd call it a calculation, or what would you call this? This procedure that we're going to go through here is to understand, our objective is to calculate the trajectory of an alpha particle as it passes near the nucleus of a gold atom. So sometimes it would maybe here was the gold atom, maybe right there. So these particles were going, gold atom was right there. The nucleus of the gold atom was right there, and these alpha beams are going here. But every once in a while, one would pass a little closer, a little further away. So we're trying to figure out what that distance was from the nucleus. So. And we can determine that by how the trajectory changed. And we have this little map over here on 26, and it shows here the gold atom was originally here, right? The gold atom nucleus, and here's the original alpha particle, and it was originally going at like this. But because of the charge on the gold atom, as it neared, some of the particles would change trajectory, and we're going to try to figure out what that trajectory change was. Okay? Now, so the second objective is to estimate the size of a gold atom's nucleus using Geiger's data. So you could determine the size of this gold atom based upon the nucleus of this gold atom based upon how it deflected the alpha particles. Alright, so to do that, we look down here at procedure 1. Look at the figure A. The position of the alpha particle, now figure A was what we just looked at, right? Okay, that's on page 26. You can look at that while we're reading here. The position of the alpha particle and the gold atom nucleus are shown on a standard XY grid. The gold atom nucleus is located at the origin 0, 0. Assume that the gold atom nucleus is much more massive than the alpha particle, and that the position of the nucleus does not change. The initial position, so the initial position of the alpha particle is right here, all right? And the initial y of the alpha particle is representative of here. And you can look at your map, your graph. Here we go. Alpha particle, we're going to say right here on the initial x position here, and initial y position here, okay? So we're going to be figuring its trajectory along here. Alright? Trajectory of the alpha particle. Alright, to do that, let's continue reading here real quick. So, the alpha particle is initially traveling parallel to the x-axis with an x velocity represented of here. 1.500 times 10 to the 7th meters per second, and a y velocity of 0. So the y velocity being, so here we go, so that was the x velocity, so it's going this way at 1.500 times 10 to the 7th meters per second, and its y trajectory at first right here is nothing, it's 0, right? It's not going anywhere. Okay, so as it continues on, let's see what we got here. So table 1 contains initial values for x, y, v, vx, and vy. So the unknown value to determine is the final angle 0 of the A particle. The value 0 will be determined by advancing the A particle along its path. And its path, along its path at this interval. This is 1.33 times 10 to the negative 20 second intervals. So that's not like 1001. No, it's 1.33 times 10 to the negative 20th per second interval. So we're talking real fast. So then we're going to plot the initial position of the gold atom nucleus and the alpha particle in figure B. So when we're all done with these figures, you need to plot it here on table page 26, figure B. You can start plotting it as you go, or you can wait till you're done, or you can use the Google Docs to plot that if you like. Note that on this figure, like right here, y position times 10 to the negative 13 meters. So this is, for instance, 1 times 10 to the negative 13. Okay? And same thing goes for the x position over here. Okay? Now, let's see, where are we at? Okay, so let's go back to, here we go. So the first thing you need to do, step, is to calculate the distance r between the gold atoms. And that was on your table, page, there we go. So, this table right here, we're going to figure out right here, we need to figure out distance between particles r. Okay, so that's the first step we need to do. Alright, and the first step, let's go to my sheet here and we'll calculate. So you can follow along step 2 and then continue on to step 3 and etc. in your book. However, I wrote it out just a little bit different, and you have a Google Doc that I took a picture of this so you can see it if you like. So here we go. So first, for table 1, find the distance between particles r that we just pointed out. Okay, the distance r is the distance between the gold atom nucleus and the alpha particle, and use this formula that we just showed on step 2, right? Okay, the trick is getting it into your calculator correctly. Okay, so put it into your calculator as follows. So you're going to hit square root right here. Let's see if we can do this. Square root, then you take x. We got the x value from the table. So you got the square root. Now you need a parentheses here. This parentheses, you're not going to close it until the very end. Don't forget to close it at the very end. Next, you need a parentheses. So it's order operations. You need to tell the calculator what to do first. And the first thing you need to do is what's in these parentheses, right? And then the second thing is in these parentheses. And then the third thing is in the outside parentheses. It's going to do what's outside these first, and then it's going to do what's inside. Inside, outside. Okay, so first of all, you got parentheses, parentheses, -6. You put that in there times. This is representative times 10, and most calculators look like this. Times 10, and it usually gives you a parentheses, -13. I would recommend just putting it in parentheses anyway. -13, make sure you close out that parentheses, then you do another parentheses, and don't forget to square it. Okay? Then plus parentheses, and you got your y value right here. You plug that into your calculator, make sure you do it like this. You got parentheses around there, -13, and make sure you close that out, do your next parentheses, square it, and then you got your parentheses, okay? And then r equals 6.325 times 10 to the negative 13th meters. So then you plug that into your table right here, right? Okay? Next step is, second thing, we need to find the final velocity, right? So we need to find the final velocity, which is right here on this table right there. Change in y velocity. Okay, to do that we go to step 3 on page 26, which is right here. Find the y velocity. Now remember that this little triangle here means this means change. So the change in something. The change in is what it means. So change in v is velocity y in meters per second. Now the meters per second, this is only a unit, okay? So you can follow along this formula on page number 3, page 26. here's our formula. Okay, it gives you the formula. It gives you the velocity meters per second. Let's see, what is that velocity? It tells you in the book. Oh, here we go. Right here. This is the proportionality constant, which accounts for the charges of the particles and the time interval used. Okay. So this is represented here, 7.311 times 10 to the negative 20th. Now this right here again is this is only a unit right here. This is meters cubed per second. Okay. And then we have multiplied by 1 divided by r squared. And now you guys just figured that r comes from the table. That's the r value, this r value right here. Okay. You need to r value square it times the y, which is the y position, which you got from your table, which you get from your table right there, y position. Okay. Then you divide that again by r. And okay, so now the important thing to do, let's see, what would I have here? This is the, so this factor right here, the 1 divided by r squared, this is the electrostatic repulsion force on the alpha particle by the gold atom nucleus. So, if you want to look back at it here, that's the force that this gold atom here is putting on that particle. This is the force that it's putting on there, the electrostatic force. Okay, or electrostatic repulsion. So there's a little from the positive charges in the nucleus of the gold atom. Okay, that's what that's determining. Now, don't worry, a lot of this stuff is still, it's hard to wrap your mind around all this. Frankly, I still have a hard time wrapping my mind around. So let's just do the best we can. Okay? So now, the more important thing is to learn how to enter this into your calculator. Well, important thing at the moment. Okay, so down here, we have, let's see, that's looking here. Okay. So if we look, where are we at here? I'm trying to get my camera right. Okay. So, this formula here, this is how you put in your calculator. Make sure you get a parentheses. Now there's a parentheses starts here and it ends all the way down there. Alright? So you got parentheses, parentheses, and then you got your, what do we call this? We call this the proportionality constant. So your proportionality constant, 7.311 times 10, and do this. This is how it looks in your calculator. Some calculators will give you a parentheses minus 20 minus 10 to 7.311 times 10 to the negative 20. Make sure you put the parentheses after the 20. Make sure you do your next parentheses. So now you got this all nicely in one parentheses. Then you multiply that by 1 divided by, now this is very, very important. Your r squared has to be in parentheses. So r, you got a parentheses, and then you got your r value. This is your r value. Make sure you print your parentheses afterwards. Another parenthesis closing out. Then square that, and then another parentheses. So this right here is representative of this right here. Okay? Okay, then you want to do, now next we got to do this representation, which is the y divided by r. So you're going to take it parentheses, and then another parentheses, because you need this to be in parentheses, your y value, 2.000 times 10 to the negative 13. Make sure you close out the negative 13 parentheses. Then you close out this parentheses that was started right there. Okay, then this is your division, divided by another parentheses, and then you have your r value. Okay, just like we did before, parentheses. Here's where it gets strange. You got this parentheses is closing out this parentheses. This parentheses is closing out this division parentheses. And then you need another one way on the outside. So it seems kind of strange. You got 4 parentheses right there. So whenever you have a trouble, you're in a computation, look and see if you got the parentheses right. Okay, so then that gives us the change in v, change in velocity of y will equal this long number here, right? 57786.3402. Well, you need to convert that to at least 4 significant digits. It tells you that in number 2, I think, on page 25. And so when we do it that way, the change in velocity y equals 5.779 times 10 to the 4th meters per second. Well, why 9? Well, you need to round that up, right? 5 or more, round up. Okay,